today would like to make a little bit of a a journey into what every one of us is talking about. The role of robotics, digital technologies, and AI. Okay, that is becoming very quickly in our lives. And so, what is the implication of this on our biological sciences, in ecology, in environment? These two words seems to be decoupled because we have on one hand the high-tech freak robots, and on the other hand we have forests, biodiversity, land, agriculture, food. In which way these two things are connected, biology and cybernetics? And so, okay, let's start our journey. Okay. Okay, let's start again from the first part that I want to say about global changes, because changes are occurring very rapidly now, but change also occurred in the past of our planet, more slowly, of course, now we're accelerating, but there have been changes. So it's not true that our planet was always the same. And this is, I think, a very interesting observation that was made firstly by James Lovelock, when he's a chemistry professor and became also an ecologist. Probably you remember the Gaia theory. Looking at the atmospheric composition of planets near our Earth, and you can see immediately something anomalous, because you have a lot of CO2, almost the same between Venus and Mars, more or less the same magnitude. Oxygen is very low, actually, very, very minor, and also a little bit less of H2O, water vapor. So in the land, in the Earth, you can see we have much less CO2, a lot of nitrogen, a lot of oxygen, a little more water vapor. Why? This was the first question that James Lovelock took. And in all these planets, we have a chemical equilibrium, basically, in Mars and Venus. We have this equilibrium in the Earth. This equilibrium is due to the biology, to the fact that we have other chemical processes, transformation, that are not described by the physical-chemical equilibrium, that are due to biology. And this is why they came out with this Gaia hypothesis. James Lovelock was very interesting, although I have to say that there was a little bit of debate between James Lovelock Gaia hypothesis and the Vladimir Vernadsky theory on noosphere. I don't know if you have heard of Vladimir Vernadsky. He was an Ukrainian researcher, professor, that he, for the first time, actually, before James Lovelock, have let's say, discussed the potential of the planet as a biologic superorganism, as the Gaia hypothesis was saying later on. So we have to give a tribute to Vladimir Vernadsky as well. There's actually a little of an anecdote on this part, because I was a member of the EGU Bioscience Medal Committee, and the first medal we wanted to attribute to Vladimir Vernadsky, okay, as inventor of the biosphere, atmosphere coupling, and so on. And we wanted that the medal, well, actually, the medal was entitled the Vladimir Vernadsky Medal. And I want to give to James Lovelock, but James Lovelock refused to get the medal because he didn't want to be, behind Vladimir Vernadsky. Okay, so this is just a little of anecdote in the scientific community. And that's the very interesting experiment that is very old paper has been published. This is a DAISY word. You can be a little bit shocked by that, but the Andy Watson and James Lovelock. Andy Watson was a postdoc of James Lovelock. Imagine a planet in the sun, let's say, orbit, with only two organisms, two daisy, okay? These are two daisies, one black and one white. And they simulated their equilibrium across a range of solar irradiation. So, okay? This is the change in solar radiation. And what happens? They have a similar behavior in terms of growth. They depends, the daisy, on their growth, on the local temperatures. They have kind of parabolic behavior, so they have an optimum, okay? And at a low temperature, of course, they don't grow anymore. They decay, and also they are killed at a high temperature. So what is different? The difference is that black daisy have an albedo very low, so they absorb a lot of energy. and the white daisy, they reflect a lot of energy. And so they started to play with the solar radiation going to the planet. And what happened is that you can see that in their model, across all the different irradiation energy coming, the temperature remain almost constant of the planet. So this means that the two systems regulate with feedbacks that the black survive when there is a low energy, because they have black, they can warm up and they can reach their growth rates. The white survive when there is a lot of energy, because they are white, they reflect a lot of radiation, and so they can survive because they're cooling. So this is the way which planet function with biology. Okay, it's possible that there are systems that feedback continuously together and maintain the same situation. The stability of our planet, in this case, the planet of Daisy, was given by the feedbacks between organisms. And then this comes back to the point of the biosphere-atmosphere evolution. That's another great example of how the physical environment has evolved with biological environment in the past of our historical development of the planet, where the atmosphere was very rich on carbon dioxide at beginnings by 4.5 billions of years ago. And then something happened in about 3.8, 3.9 billions years ago in production of methane. Archaeobacteria produce methane. Methane was very important. Why? Because they basically produce a little bit of cooling and carbon dioxide that was decreasing very much at that time. Then there was the big oxygen production that was due to cyanobacteria. Cyanobacteria start to produce a lot of oxygen, and now this oxygen we already have in our atmosphere. Then the plant came in and increased again with photosynthesis, terrestrial photosynthesis, the oxygen, and the carbon dioxide decreased very much. So the evolution of the entire atmosphere was driven in the last 4 billion years by the chemistry of the biological organisms. So this is an example of how the two systems, atmosphere, biosphere, are coupled, they co-evolve together. And then we arrive to today. Today we know that there is a big feedback of, for example, terrestrial land. This is a simulation that we made based on flux towers, measuring carbon dioxide fluxes and reconstructing GPP, so gross primary productivity of terrestrial land. And you can see seasonality very clearly, of course. The tropical regions remain always active in terms of photosynthesis, and the ocean. The ocean also very important in taking up carbon, the different mechanisms, biological and physics mechanisms, but both contribute almost equally to 30% of carbon dioxide emission reduction. So they absorb 30%, but about 50 to 60% of the carbon that we put in the atmosphere are absorbed by terrestrial and ocean ecosystems. So this is an important feedback, because this maintains the level of CO2 lower than it would be without this biological activity. And then comes the humans. The humans are, so far we had, biology, let's say, not humans. Then comes the humans and change again the planet. And the humans are particularly active. You see, everything happens more or less in the last 60, 70 years with growth of population that started this exponential growth very, very quickly. Just to consider that at 0 means this is the form of Jesus Christ born, a calendar. Only 250 million were living in our planet. So we are a big planet just with 250 million people. That's very small. And then it started to grow very much. Particularly look at this. I'm particularly curious because I was born in 1959. Okay, I'm about here, and I can say that in my life I have seen more than doubling the global population. That was unprecedented. totally unprecedented. The first generation that the 60 was absolutely seeing this great population. Now we're heading to 9 billion, okay, 2050. But the quality of population is changing also very rapidly. We have more urban people. 80% of people will live by 2050 in cities, and the rural population is declining, as you can see. So we 2010 we reached the equal number. Now we are much more citizens than farmers. Okay, this with a lot of implication in terms of how we're going to use the resources and how we produce food. Who's going to produce food in the future if everybody stays in the cities? Is a big transformation on also processing technologies, way of lives. Is a big change. Then, of course, the population growth has impacted very much the planet. So again, we have another force in the planetary evolution, that is the humanity, that shape resources, change things. This is the, for example, the area of forest that has been destroyed in the last 8,000 years ago. 8,000 years ago, there was these gray regions here were full of forests, pristine forests. And today, the pristine forests just remain in these little areas in boreal regions, in Southeast Asia, and of course, Equatorial Africa and Amazonas. So we have destroyed the forests to make agriculture, to produce food for giving food to the growing population. And we can say today that we have used 73% of the total land, excluding ice, as for human needs. We have left only 27% for the future citizens, for the future humans. It's a little bit less, it's a bit low, let's say. And deforestation proceeds at 30 million hectares per year. You can see here. Italian forest area, just to give you an idea, is something like 9 to 10 million of hectares. So more than Italian forests every year disappear from the planet. So it's really impressive. Of course, oceanification, that's also another phenomena of the human impacts and the warming of the oceans. And then, of course, the decline in marine biodiversity, just as an example, as well as terrestrial biodiversities are affected. Then we have also some paradoxes that is something that is coming out recently because when talk about climate change and the energy, we are, of course, concentrating on fossil fuels, greenhouse gas emissions. But what about food? Food is the energy that we use as humans to live. And they have an impact. They have an impact, but in a different paradox way. Because, for example, we have 868 million people that is without food. This is the first paradox. 1.5 billion that are obese. They eat too much. So this is a paradox because at the end of the year, we have more or less the same amount of people that are dying for disease like cardiovascular disease or diabetes. Diabetes is an emerging big disease, especially not only in developed but also in developing countries. In Africa, diabetes is a major force of disease, and so it's very strange that we eat too much or eat too low, and in any case we die altogether. We are the same boat, we can say. Also, again, the grain production and the effects of animal proteins is an important change in the last 68 years. We need protein, animal proteins. We have to convert the land to produce the feedstock to feed the cows and give them the food to produce proteins. And this is ecologically, energetically, is a loss of energy because you have to create a lot of land to produce something that you don't eat directly, but you go to another organism. And so we have created an impact from the meat production. And at the same time, now we're also talking about biofuels, so using land for biofuels, and that again very strange because we don't have land. So at some point we have to decide if we want to have a lunch or to have a car drive somewhere. We have to decide of this. And finally, the food waste. I don't know how much this is considered here in Hong Kong, but in Europe is a big thing, is a big problem. We have more than 35% of waste of food. Again, is an ethical problem. People is without food and we waste the food. And then is also an ecological problem because we cultivate land, but use less because we don't use the food. We throw away the food. So we use land that is very precious, as we said before, producing greenhouse gas emissions, water, energy consumption, but for nothing. That's absolutely something that we cannot allow. And of course, we have also these metrics are starting to appear. This is a paper about the amount of carbon footprint associated. It's very popular, became very popular. This paper published some years ago with quite a number of items, 30,000 food items for carbon footprint and for water footprint about 1,000. So we have now a better knowledge of the total life cycle assessment of this food, and we can say that there is an impact. In fact, the IPCC report on land and climate for the first time say, guys, wait a minute, we have a problem with food, okay? It's not only electricity, it's not only mobility, greenhouse gas emissions associated with food are important, because if you consider all the entire chain from land use, okay, so conversion and deforestation to the greenhouse gas emission emitted by agricultural production to processing, transport, packaging, retail, cooking, and whatever, waste, at the end you arrive to a number that is absolutely relevant, is of the same size of the electricity impact, okay, on climate change, on greenhouse gas emissions. So it's very huge. So we need to do something about this. It is very interesting, and we are discussing at lunch with Charles how to calculate for the China diet, or for us, we have calculated these things, but there's very few numbers about this information on, and we'll be very interested to compare. And then, of course, climate change is part of the human impact. So the humans have been so strong in shaping the planet, and we have this climate effects these days. Yesterday, I was interviewed by Italian journalists. Yesterday evening, I was visiting the fisherman village that I told you, what's the name of it? Tauho. And I was 1 hour at the telephone because he wanted to ask me about what's going on in Europe. In Europe, we are now very unusual, probably the hottest extremes we had in the last century, okay, in Paris, in Rome, in Spain. And that's okay. This is what's because of the humans, okay, because we have altered, we have changed, we have modified the atmosphere. You can see these are just the temperature anomalies. That is not equal. You can see it's really changing across the globe. And for example, the northern boreal regions are very much heating compared to others. And of course, this is due to CO2, carbon dioxide. We measure carbon dioxide, thanks. This is a satellite column of CO2 concentration measured by OCO satellite. And you can see that it's very clear. This is the northern hemisphere where most of the industrial activities are going on. And you can see the red, it means a lot of concentration. But we see a lot of things. You see also here in Africa, in the equatorial, in the Congo River basin, the red plumes. These are savanna fires and forest fires due to deforestation. They are very evident. We can see from the atmosphere. We can see also the Amazonas at some point due to seasonality shift. We can see here also, the plumes coming from forests. So we know almost everything, let's say. Changes in peak concentration is also very stable, let's say, is growing year by year without any sign of inversion. And then, okay, we call this Anthropocene. Welcome to the Anthropocene. Is the age dominated by humans. All the indicators you see here are exponential. We live in exponential world. Okay, it's not good, because if you remember, some of you are mostly, I think, physicists or engineers, but Malthus was one of the great ecologists with the famous equation of the population growth that cannot be exponential, there should be at some point sigmoid. So we are in the exponential phase. So it's really terrible. It's very dangerous. We are not in a stable, let's say, stationary system. So that means that you see all the indicators in terms of water use, fertilizer, McDonald's, restaurants, ocean ecosystem damages, and so on. Everything is going up. And of course, this is the result of also geospatial changes, great geospatial change. You are expert of geospatial science. You see from your satellites and so on, what's going on very rapidly. Every year you can see things moving, and these are just example of how the flights are basically are everywhere in the world. Urbanization lights, these are the lights, are very famous picture of light during the night, and you see how we have explored every little piece of our land, basically, and we try and transport and trade. So the humans are dominating very much our planet. And now it comes the point. Are we entering in a new change again? So far, we had the classic geoscience changes, biological. Then we had the humans, we call that Anthropocene. Do we have something that we call, Cyberocene, something that is due to the big change, the fast change in technologies, in AI, robotics? Is something new happening? What will be the impact of these transformations on our ecosystems, on our planet? Is our planet changing? Is our humanity changing? Okay, I'll try to provide you some reflections on this, okay? First of all, the data are really striking. We have Internet of Things devices that are now populating the world. We have, in 2025, we had something like 75 billions of sensors connected in real time, in parallel, continuously. So we measure now a lot, but it's still growing. We're still continuing to have possibility to monitor, to sense our environment, our planet. It's growing very fast. Then we have came to the machine automation, the sensors, the electronics, the microcontroller became very popular. And so we started to have machines that are autonomous. So we give programs, they can do laser cuttings, mounting SD components, 3D printing, and numerical control machine for producing metal pieces and so on. And then we had the AI, the next step. So far, those machines were quite stupid, okay? They were just programmed by simple coding. Now we have AI. So we can talk with an entity. We can, the entity can respond to our questions. The entity store all the human knowledge, okay? What has been done in the last years is to collect a huge amount of information contained in the web, scraping the web. Sometimes we're infringing also intellectual properties, that's what I have to say, without paying back the intellectual properties of many people, of people writing literature, people, producing papers. And that is now the availability of everyone using generative LL large language models, or more recently, and now trending now, foundation models, multi-agent, using different data sources, images, data coming from different ways and sources. And of course, the robotics come to play, because these two things, the machinery, automation, and the intelligence, both are a terrific mixing, because you can give the intelligence to the machine, to humanoids, to robots. And today, so we can say that very soon, we can see every week, some new advances. This was recently humanoid schemes made by silicons are very, very similar to our schemes. You are in the middle of these things. Shenzhen is, I was in Shenzhen 2 days ago, and I had exactly this view. And so we have to deal with this. Are these humanoids? Are these new entities, new organisms, cybernetic organisms that will come to play in our planet? They will start to use resources. To what extent, or maybe not? Okay, and let's go back a little bit to the other side of the story. There is nature. There is nature, and there is the possibility that the biological world can tell us a lot in terms of cybernetics, okay? Now I'm trying to show you the similarities, the convergence of biological organisms and cybernetic organisms, and see that could be possible that the way we will see a new transition. First of all, are they similar? Well, if you look at many examples, this is an example of a microprocessor, okay, with digital lines connecting to the outside, sending out information of course, in digital format. And this is a neuron and the dendrites, and these are doing the same thing. They are changing information with other neurons. Electrical potentials are flowing there. Information is flowing. Information is the same thing. Information is moving in both systems. And not only information in a sense that we transmit information, but also we elaborate information, because the neuron, well, as you can imagine, is very similar to a neural node where you have different, let's say, stimulus inputs, a function for using aggregating, and then an output that can be transmitted. And this neuron basically can be assimilated also to a controller that can information, elaborate, and give back this information. Can they co-evolve? That's an interesting question. The evolution in biology is mostly through DNA replication, okay? Genetics, very important role. We know DNA, we know that all our life is based on an informatic system, indeed. Very, very interesting and very specialized informatic system, where we have 4 bases that can stick together, and then we replicate the information by DNA replication. These bases are very similar. You can encode the bases into bits, okay? And you can represent, for example, the 4 bases with 2 bits, okay, to the second, and this is 0, 0, 0, 1, 1, 0, 1, 1. Not only that, but they all the time they stick together, they undergo a typical informatic operation that is a negation, a complement. So it means that the base A attached to the base T, okay? This is the only way to do it. And the base G to G. And you can, if you look at this binary operation, this absolutely is an inversion. So you have that 0 and 1 and 0 and 1 and so on, you see? So this is what the computers, they do, basically. So it's very easy. They use a binary language information to attach one to another. And so now the question is, how much information is contained in biological organisms? If you know now that how we can code the biological information in DNA and bases, how much information then the biological organisms contain? This is a RNA, the RNA of a virus, and we can encode this in about 2.5 kilobytes. So 2.5 kilobytes can represent the information contained in a viral RNA. For bacteria or DNA, it's more complex. You need 1.5 megabytes to contain the information. The human genome has been, as you know, classified, and so we have now about 750 megabytes. Is it really interesting that you can carry your own genome in a pen drive? So this is your genome in my pen drive, okay? That's very fascinating. And if you take all the languages, this is an analog system, all the languages of the world, including dialects, again, they can stay in a pen drive. It's 1.6 gigabytes. So it's not so much. This is why we are so impressed when we see AI so fast, in what they are doing. In reality, okay, they use billions of parameters to tokenization, so on. But in reality, the amount of information they really look at is not so big. It's not so big. The language, I'm thinking about the language, okay? The way you combine the words can be, okay, exponential in terms of probability, but the amount of data that is working on is absolutely trivial. And of course, you have your PC on the table that is 1 terabyte, okay? Much more than the biological organism, okay? But, so it seems that we have, let's say, a predominance of informatics into the biology in terms of information storage. But this is a very interesting paper that appeared some years ago that is post-published in Trends in Ecology Evolution, that was why quite inspiring, because they try to calculate how much information in bytes is contained in different organisms in the biosphere, okay? And they used the same argument I used before, okay, to calculate this. And so let's start from about 3.8, okay, channel, let's say archaeobacteria, and then I will see before along the other organism. You can see that at the beginning, of course, there was a great increase of information, because speciation, formation of new species, occurred at very high rates, and then stabilized, okay, at this level. These are the humans, okay? They started to appear more or less 100,000 years ago, and then again we had the speciation and genetic information transfer, and then more or less we are saturating. This is the language, and the analogical part, the language, and we are declining because we don't use any more books and so on. The language is also declining, and that is the data center. Data center up to 2024, I think was this paper. So what we can say, that in reality, if you look at the total information storage in nature, is still predominant. Nature still contains the most of information in our planet, 10 to 37 bytes, if you include all these biological organisms. The digital storage up to 2025 today contain 10 to 23 bytes. So there are 14 order of magnitude between nature and the data centers, okay? So still, nature can tell a lot, still. If you look at the information throughput, so the velocity in which information is changed per second, bytes per second during these transformations, and we compare, okay, human DNA replication is the highest rate. I'm sorry, no, the bacteria actually, the bacteria are the highest rate, 10 to 28 bytes per second. So in every second, we are replicating our cells, okay? What you see here is exactly what's going on in our, and these are the number for global, not for individuals. And you can see that still you have these very high throughput rates. I put here the tree because I'm very, fond of trees. So it's still very good in terms of velocity of information transformation. And the data centers are quite slow, 10 to 15 bytes per second, what today they are changing, okay? But the big difference between these two is that in one case, we have a lot of energy. You see, these are the fossil fuel and so on. Data centers are very hungry of energy, fossil energy still. And everything here in the biology starts from the sun. It's for free. It's the sun that makes everything, the machinery working. All our machinery, all our evolution is just given by the sun. So it's a big difference. And indeed, okay, this is another interesting fact. The energy is very important. It's very important in evolution and informatics and evolution. So this is the Landauer theorem that say that you have a minimum of energy irreversible. So there's not less than that to process one bit of information. This is a theorem. If you're interested, you can go deep. So you have 3 times 10 to minus 21 joule per bit. So this is a kind of fixed limit. You can go below this. If you calculate the energy that is involved in these information systems, DNA is very efficient. You see that 10 to minus 15 power in watts. So it's distance from the limit 10 to times 4, 100 times. Human brain consumes 20 watts. Our brain is 20 watts, less than a lamp. So very efficient. If you think, you can imagine how much information you every day, when you wake up in the morning, drink your cup of coffee, and decide what you have to do, it's only 20 watts, and a lamp barely illuminating your room. It's nice. It's nice to see this really very high efficiency. And the GPUs, of course, are quite inefficient, 700 watts. And so they are very distant from the Landauer limit. Then now we come to but what is the real difference between the biological and artificial intelligence? I think there is a lot of work to do and a lot to learn from nature. First of all, the digital artificial intelligence is pretty much deterministic, okay? It's going through a clock, the driven microcontroller, and the instructions are sequentially determined and so on, with fixed algorithms, okay? With fixed algorithms. In nature, things change all the time. We have our intelligence, our way to process information is very adaptive. We learn from the past. We learn from mistakes, not only from mistakes, but we learn from implausible things. Sometimes we think things that are crazy. Of course, in that moment, we discard this information because it's not attached to the reality, but we keep memory of this crazy thing. And this is the intelligence, the capacity to evolve and produce new information. This capacity of producing new information doesn't hold in AI. AI cannot maintain the crazy things in memory and taking back when they need, okay? They have to cut out, like, the Bayesian system, they have to cut out what is noise. And there are many examples of adaptive intelligence from, the human brains, the octopus system is very intelligent, adapting. I think I like very much the mycelium of fungal because they have a really large network of organisms that are connected all together, and they can collectively respond and process the information. Also, the immune system, our immune system is a fantastic machinery because, as you can imagine, that we are born with a legacy with our mother, okay? For the first, what our native immune system is given by, and then we learn to fight against everything new, and we adapt all the time. We change our protein, our mechanism, adapt continuously and learn continuously. So this is something that still has to be difficult to replicate in machinery, and so on. There are many examples on that. And this also comes to the point that maybe in the future, we probably have to move out from this digital deterministic way that is working with bits, 0, 1. That means we simplify the reality because we don't have anything between 0 and 1 in this moment. We just have to accept that everything can be tokenized, can be discretized, and that is very much different to having an analogous signal where there's a rational number that can go from in any direction. So you can appreciate even the smaller changes. And this is what really let's say the real biological system, through changing their, of course, electrical potentials in their systems and chemistry, they are more similar to analog system. And that now actually this analog computing is becoming reality. They're starting to produce computer with analog processing. And we have to look at this as more close to the nature as before, compared to before systems. Then I've closed this, let's say, conversation with, first of all, my team here, we have been discussing a lot how we could apply some of this concept of biological organism in a cybernetic way, how we can find similarities. This Francesco here, and Cinzia, I don't know how she's went because she has a cold, okay? And when we're talking about how to reproduce these functions, they're very complex, you see, photosynthesis, respiration, evaporation, transpiration, soil, and so on, genetics, replication, into something that we could study from the cybernetic point of view. So we can transfer this into cybernetic organism. And they started to produce some technology. This is why we discussed with Charles a lot last time about this new sensor that produce every hour a lot of information about the different physiological function of the tree. So we are basically creating a physiological digital twin of the tree, where we measure water fluxes, spectral light from leaves, say moisture, diameter, growth, so biomass, and also even stability. And with different techniques, these are different way, everything in one single device. This is, for example, the water flow rate, during the day, during the night, and so on. So this very nice, symmetrical and regular flux that could have also anomalies, and this is why we're interested to understand the anomalies on these regular patterns. as well as these are the growth we measure every hour with a very high resolution, 0.43 micron. So we can see very, very small changes, even the water swelling and shrinking due to the moisture of the trees and the tissues. And of course, the spectrometry that we have also developed, our own spectrometer we discussed in the lab, is very small, as you can see. These are 4 chips that are covering 28 bands in the 400 to 940 nanometers. And we use to detect, changes in color, and that's very important, as well as seasonal changes. For now, we have a very nice growing season detection. So you know exactly which days leaves are out. This is an example where the leaves are out. Because interesting, in this area or here, trees are not the same. Some trees leaf out maybe 1 week later, other 1 week before. The Sakura effect is, I know, I'm sure you know very well, is, okay, we can say it's in around 2 weeks, but with many differences between trees. Why? Why the trees are so different in leafing out and leafing down? So that's an interesting physiological and biological question. And then we come to the to use, of course, this information. We have now more than 6,000 trees. We monitor continuously every hour in different places in the world, and we are growing. We're trying to establish more and more. Yeah, we have great ambition. We want to monitor all the trees of the world. Okay, not all, but a great number in different forests, and try to use more or less this concept of a tree as a neural node that basically elaborate information from the environment, from climate, from different processes. Even we could construct some 2-dimensional networks where the trees are also talking each other in terms of proximity and competition and roots communication. So we are trying to model also this part of inter-tree communication and try, okay, this we can skip, using this representation to run in parallel a huge number of trees, okay, and that's okay. How many trees we can run? Okay, in the moment we are 6,000, but globally, there are 3,000 billion of trees. This is true. It is measured by LiDAR. It's been measured by this was a Nature paper, actually. You can ask why Nature published a paper like this, because what is the goal? That you have to remeasure the next year and see how many trees are died or so. No, I'm joking. It was a nice paper, however, because we didn't know how many trees there were in the world. So it's good information at least. So we know there's something around 3,000 billions, 3,000 billions of trees. Yes. And so maybe yes, we can monitor with the IoT sensors, low cost. And you can calculate how much costs in terms of computing. It's not so much. Basically, we need someone that give us the money to buy 16 GPUs. Not yet found. We have only for the moment 2. It's still enough for our 6,000 trees. More than enough, but we have to find an investor for 16 GPUs to run our models. And then the final conclusion. The final conclusion is we are now moving in another time. There is another time in front of us. That's true. The time of the digital world, the time of artificial intelligence. And we are scared about this because we think we are changing completely our way of thinking of biology, and we will be extinguished as a species or something like that. But in reality, I more think that we are co-evolving. We are co-evolving. This means that possibly, and we will see already in practice, there are people with heart pumps made by silicons or arms and legs with exoskeletons that they can run. So we are moving, in something else. We are moving something else. And this is good or bad. I don't know, but certainly it's still humans that evolve. We have to co-evolve with this. Still remain one problem: the energy. All the organisms, even the cybernetic organisms, require energy. Humans require food for energy. cybernetic also requires energy, and so far energy is coming from fossil, and there will be no evolution if the energy will not be renewable. That's the future of the planet. Because at some point the fossil fuels will finish, and even the cybernetic organisms will die. So the future will be basically on what energy we will able to afford that is totally renewable. Thanks.